For our senior design project, we will be creating an IR finger vein imaging scanner for the purposes of security clearance. We have 2 computer engineering majors, Emmanuel and Jordan, 2 photonics majors, Jessica and Francisco, and an electrical engineering major, Benjamin.
The development of the project started on defining the areas where we were interested in working on. We found that security and personal authentication were a common denominator to work on. Therefore, we start to look at existing products in the market. The most common identification devices are keypads, scanners, and card readers. However, we found that keypads and scanners require the user to have direct contact with the device. Even though card readers don't need contact, the ID can be easily stolen or lost, which compromises the identification process. We found on those deficiencies the opportunity to develop something better. Our objective was to design a device that is contactless and secure. The solution to our problem was to use biometrics as an identification card. We consider the 3 main biometrics: fingerprints, iris scanners, and vein patterns. Even though all of them have shown a high level of security, fingerprints require to have contact, while iris recognition can generate discomfort in the user for the proximity and the movement required. However, not everything was perfect with vein patterns, since this technology don't have as much research as fingerprint scanners do.
Our project, the IR Finger Vein Imaging for Security system, works by having a user place their hand in our housing. While the user places their hand in the housing, the bottom portion is the imaging acquisition portion of the project. We will then start taking images. You can see the camera and the lighting system and the mirrors. So the images taken in this part are ran through the nano and then used through the machine learning part of the process, where then a projector gives you the feedback of whether it is scanning, has taken the picture, or the user has failed or successfully been identified by the system. During this time, the user also has the ability to give hand commands, and the projector will give you live feedback on the commands as well. In order to reach our project overview vision, a few project objectives were set up from the beginning. On the photonic engineering side, they're using infrared speckle pattern imaging to increase the contrast in an image, camera and lenses for magnification of images, a projector for displaying the images, and a hardware assembly for both imaging and projection sides of the photonic engineering. On the computer engineering side, they're working on image processing for enhancement, image pattern identification, HMI for new user inputs, user direction messages, and vein layout processed imaging. Finally, on the electrical side, they're working on power supply, PCB designs, and wiring diagrams.
Here's a high-level overview of the project's implementations and their corresponding fields. Hello, my name is Jordan Pena, and Emmanuel Cortez and I will be discussing the software on the NVIDIA Jetson Nano and the machine learning. Here we will talk about the hardware comparison between the NVIDIA Jetson Nano and the Raspberry Pi 4. Both NVIDIA Jetson Nano and Raspberry Pi 4 have ARM-based processors that run at similar frequencies. The Jetson Nano has a much more powerful Maxwell-based GPU, but the Raspberry Pi 4 has higher RAM space. The Nano had a total of 3 USB ports, and the Raspberry Pi has 4 USB ports. But we chose the NVIDIA Jetson Nano over the Raspberry Pi because at the time of purchasing, they were similar in pricing due to a global chip shortage, and the Jetson Nano has a much more powerful GPU, which is essential as our project relies more on GPU performance.
From the point of view of the software, we can think about it as two different systems or softwares working together. One will be the processing of commands, and the other one will be the execution of the machine learning. For commands, we have available the sign up and login. These commands are achieved using Python, OpenCV, and MediaPipe, where we intake a webcam image and we display menu images based on the state and process the commands at the same time. The hand capture is done using MediaPipe, where we pass the image captured by the webcam to the library. The library provides us with a way to identify what are called landmarks, which essentially are the red dots, which are in our hands would be knuckles, fingertips, and so on. And based on that information, we can do some calculations to figure out when a finger is extended completely. Once we know that a finger is extended completely, we can, based on the hand configuration or which fingers are extended, we can devise input commands. So going over the commands, let's first look at the sign up. Before we can even do the sign up, we need to be provided with a QR code. The QR code is used as a security method, so not everybody can sign up. Once the QR code has been scanned by the webcam, the user can place their hand, just as we see in the image, and begin set up timers. The timers provide the user with a moment for them to align their hands based on block images that they see. Once the timers have concluded, we will begin the capturing of images using the sensor, which those images are at the end stored locally, so that we can validate the user whenever they want to log in the future. Continuing with the command of logging in, the way it works is by extending only the index and middle finger. Once the webcam sees that configuration, it will begin a set of timers, which will prompt images for the user to align a set of blocks. Once the timer has concluded, we will begin the start of image capturing. Those images that are captured are sent to the machine learning, and based on the machine learning results, we display a success or failure message, and once it's done, we delete the recently captured images of the user trying to log in.
The authentication portion of the project is done by using a one-shot Siamese neural network. This neural network takes in 2 images for the input and will return a similarity score, instead of classifying the image directly, like in more traditional image recognition software. This is implemented by using TensorFlow and Keras, and the pre-image processing is done by Pillow and OpenCV. The machine learning dataset we are going to use for training purposes is the FMUSM dataset from Dr. Razdi from the University of Sains, Malaysia, with written consent. There were 2 sessions conducted, both having the same individuals. Each session contains 123 classes and 6 images for both index and middle fingers on both hands, resulting in a total of 2,952 images.
My name's Benjamin Wangren. I'm an electrical engineer here at UCF, and my role in this project is to develop the PCB and manage the hardware connections between its components. The PCB will supply power to the device's MCU, IR LED driver, and the device's projector. The overall PCB schematic can be seen here. This was designed using EagleCAD software, and the overall intention for this PCB is to act as a voltage converter, which will take wall power and convert it into storable energy in our lithium-ion batteries, which can then be used when needed to power on our device in the output DC voltages. The chip chosen to drive our battery-powered circuit is a Texas Instrument TLV62585 PD-RLT high-efficiency step-down converter. This was chosen for its high efficiency rating and market availability. It is recommended for battery-powered applications, making it ideal for the circuit. The function of this end of the PCB is to act as a battery charger. What this does is it takes an input of 5 volts DC from your average device charger and our micro USB port on the left and converts it into a 3.6 DC voltage, which can be used to charge and store power in our batteries, which are located on the right of the schematic. The chip chosen for our voltage output circuits is a Texas Instrument TPS 61178 RNWR fully integrated sync boost with low disconnect. This was chosen for its market availability and voltage range, which covers the needed voltages to supply power to our device. This is rated for applications in USB type power delivery and a supply for power amplifier, making it ideal for this circuit. On this end of our PCB layout, we have a voltage converter which takes the voltage stored in our batteries at 3.6 volts DC and converts it back into a 5 volt DC output at the USB port. Also at the USB port, we have a 5-pin terminal that can be used for cooling hardware such as fans. The IR LED for this device will be connected using a driver mount. This is ideal for our case because it's USB powered, it's small in its footprint, and it has flexible placement around our device, making it easily adjustable to get the proper vein image we need using the IR light. Being that this is plug and play, if our IR LED is to go out on us, we can easily swap them out. Being that the vein imaging device is battery operated, we needed to choose a battery size that would be optimal in our PCB footprint and milliamp hour ratings. Milliamp hour ratings of a battery is directly proportional to our runtime. A smaller battery size would give us smaller milliamp hour ratings, whereas a larger battery size would give us larger milliamp hour ratings. For this device, we went with an 18650 battery for its optimal PCB footprint and milliamp hour rating. For the device's lithium-ion 18650 battery, we chose the Samsung 30Q. This is because of its market price being favorable for our overall project budget and its performance ratings in milliamp hours and internal resistance being optimal for this device.
I am Francisco Torres, and now I will present the image projector system and its components. A common way to give feedback to the user is through a display. For this project, we wanted to use a different method. The idea was to create a projector screen to provide a more immersive experience. Since the user hand is the main element of the project, we turned it into a screen for the images. The two most common projector systems are DLP and LCD. The digital light processing, it's a projection where it uses a set of microscopic mirrors to aim the light towards the screen. Even though this has a high contrast and high resolution, it needs the projector will be used to give feedback to the user of the authentication process status. Multiple components were needed to develop the projector system. First, a light source attached to a reflector to improve the illumination. Then, a polarizer together with the LCD will generate an image. And finally, the optical system will project the image into the user's hand. The lens system was formed from a Cook triplet base model. Formed by 3 lenses, the optical design focuses the image at 54.3 centimeters from the source. Starting with a 147mm focal length positive lens, followed by a negative 50mm biconcave lens, then the final image will be generated by the last 60mm focal length biconvex lens. The overall working distance was designed to be long because the system will redirect the light using mirrors to adjust the image location. The projector will be located at an approximate distance of 18 centimeters from the user's hand at the moment of the projector. Therefore, a longer working distance will guarantee that the user is able to see the projector on the hand without having any optics that might block or obstruct their view. To fit the image in the user hand, we designed the model to have a magnification of 2. That means that the LCD that is used of 3.9 inches will be bigger enough to fit in the user hand.
Hi, my name is Jessica. I'm a photonic science and engineering major, and I was responsible for the imaging acquisition portion of the project. The camera is one of the key hardware features of the entire project, and it is also the key hardware component of the imaging side of the project as well. So the camera chosen is a near-infrared camera because during the background research we found that hemoglobin is best imaged between wavelengths of 650 to 950 nanometers. Knowing that our illumination source would also end up being in the near-infrared spectrum, the camera was chosen to be able to image the near-infrared spectrum to the best of its abilities. This camera also brought drivers which made integration easier later on in the process, and because it's monochrome and it has a larger wavelength spectrum that it can image at, we didn't need to use infrared lights for every single thing that we were imaging. We're only capturing the veins on one section of the hand, so we only need to focus on imaging in infrared on that section. The Alvium 1800 monochrome near-infrared camera was chosen over the FLIR blackfly camera for a few reasons. The main ones being that the Alvium camera came with software for easy integration, and it was USB powered, as well as the price was cheaper than the FLIR blackfly camera. These 3 things were the main selling points for us leaning into the Alvium 1800 camera. Aside from that, it also has a higher resolution and a higher frame rate than the FLIR camera, which made it better while we were testing our product. For the imaging acquisition portion of the project, the lighting system had to be consistent and it had to be able to image veins. For the lighting system, we used a diode driver. We used a 780 nanometer LED from Thorlabs, which was 22 milliwatts. And then we used a collimating lens for the consistency of having the same spotlight in every single picture, and then a diffuser to get rid of the Gaussian intensity peak in each picture. The camera chosen was a near-infrared monochrome camera, and through our research we found that hemoglobin is best imaged between wavelengths of 650 and 950 nanometers. That being said, our LED had to fit both optical spectral ranges of the camera and the imaging optical qualities of hemoglobin. So we chose the 22 milliwatt 780 nanometer LED from Thorlabs. Throughout our project, we experimented with both laser and LED as lighting for our imaging system. We found that the laser with the original beam expander did work but it would take a little bit longer to process by the machine learning because the images had to be compressed on top of each other. So we decided to pick the LED in order to save some of the processing time.
For project specifications, we have a camera that can capture more than 5 megapixels of frame data and is sensitive to infrared lighting. Image lighting has a wavelength between 700 to 950 nanometers. The display has a resolution of 480 by 320 and will produce a sharp vein image. The light source will have more than 400 lumens. The CPU will process everything in less than a minute. It will have more than 2 gigabytes of storage for the database and software. Power source will be less than 70 watts and will provide sufficient power to the system. Power storage will be able to provide power for more than 4 hours.
Our project has had really good progress throughout last semester and this semester, with the majority, if not all, of the research already being completed last semester. This semester, we're really focusing on testing and prototyping. We've been prototyping the majority of this first half of Senior Design 2, and we are starting to test our components all together now in these weeks. The major things that are left to do is the casing for the assembly, but that is more on the hardware side, and we're not worried about getting that part done. We're mostly focusing our time on being able to integrate all our designs into one final system.
When it comes to difficulties from the point of view of the software, one of the difficulties was the sensor's Python library. First, the sensor isn't plug and play, which made things a lot more difficult. Second, the lack of documentation for the specific sensor when it came to the Python code. And the other thing is not being able to capture the whole hand. Due to that, the cropping had to be done manually. Another difficulty was the hardware change due to the integrate system and how sensitive it is. Any movement, any vibration could set off or could disalign the alignment between the code and the camera placement. Another one would be the multi-threaded task. Keeping control of different simultaneous executions at the same time made it a little bit complicated. And finally, I would say is RAM. RAM did slow down the process somewhat.
One of the challenges we faced when we were training the neural network was the image pre-processing. If we used just the raw images, our neural network after training had an accuracy of around 12%. Our first attempt with image processing bumped up the score to around 47%. Also around this time, we were training on our personal computers, and due to how computationally heavy it was, it took around 24 hours to complete. Eventually, we settled with using, in order, candy edge detection, dilation, and then adaptive thresholding, which resulted in around 87% accuracy. And we had also switched to using Google Colab, which sped up this process dramatically.
Some of the difficulties faced for the imaging portion of the project were the mirrors. So in the bottom left portion of this picture, we can see our mirror mounts and camera setup, and this is our final setup. Everything is set in place. But at the beginning, while we were calibrating it, any big bump into our housing would uncalibrate our mirrors, and then our image would be off or cut by our uncalibrated mirrors. So we were able to screw them in at the end and have them being a lot more resilient, but at the beginning that was something we faced problems with. Another thing that came up that we didn't know until the end was that the camera's image would end up being oversaturated or underexposed when ran through the nano. So what we were seeing on the camera software was not the same as the picture after the nano would be taking it. So we had to readjust a lot of the iris and lighting settings. And lastly, we switched from a laser diode to an LED for two main reasons. One was safety. If anybody was trying to realign the mirrors themselves or do anything on this bottom imaging portion themselves, we didn't want them to run a risk of hazard with a LED being shown into their eyes. And also for lasers being used as the lighting, then we would have to compact multiple images, and it would make the machine learning part of the process delayed even longer as it runs through the system. Some of the imaging successes, however, were that we were able to accommodate both the working distance and the field of view needed with this design for layout. Our images were able to be processed successfully for our machine learning application of whether they are verified or unverified users in the system. And the last one was that we were able to do a permanent layout for the imaging system within a confined space. So we were able to take our field of view and our optical path needed requirements and put it into a space that we were aiming for.
For the protocols, we are making use of multiple standards. We use ROS since our microcontrollers may contain LED, I2C to be able to communicate between the nano and the PCB, H.266 or H.265 for video decoding and encoding, HDMI 1.3/1.4 to project the image, IEC 61960-3 2017 to handle properly lithium-ion batteries, and USB 3.0 Type-C for power delivery.
Our budget is shared across all 5 members of our group at $250, which totals out to $1,250. From our budget listed here in this bill of materials, we come just under that at $1,025. We put the majority of our cost into our image acquisition and image processing with our Jetson Nano board and our camera.
Some of the realistic design constraints that we consider relevant are the limited budget and time, since this restricts the equipment that we can use on the system, a limited time for completing testing and developing stages. In the political side, we will be working with personally identifiable information, therefore it's important to have confidentiality